I might stop
Okay.
you a few times even. Okay. So whenever you're ready, whoever wants to start can start.
Okay. So I think I'll go first. Um, come up. Show me. Close. My eyes because this thing. Okay. Um, I want to begin right now. Can you hear me?
Yes, yeah, go for it. Okay.
All right. So good morning, everyone. My name is Obina Shekize, and I'm a master student in the Department of Chemical Engineering at A&T State University. I'll be presenting my thesis on the development of a flow raging map for slurry bubble column reactors using spectral density function analysis. Let's start off with a quick review of what a slurry bubble column reactor is. Um, this work is within the context of Fischer-Tropsch process. Over the years, basically, four Fischer-Tropsch reactor designs have been used commercially. Um, on the top, on the top right corner, on the top, on the top left, we have the multi-tubular fixed bed. We have the circulating fluidized bed on the bottom left. We have the micro channel reactor at the bottom right, and we have the slurry bubble column reactor at the top right. So this is the focus of this work. And basically, slurry bubble column reactors are simple cylindrical vertical vessels with intense interaction between gas, liquid, and solid phases. In most applications, the gas is the reactant, the reactant product is the liquid, and the catalyst is usually solid. So slurry bubble columns reactors are considered the reactor of choice for Fischer-Tropsch process or for Fischer-Tropsch synthesis because it offers an alternative source of energy and provides safe liquid fuel compared to other reactors. Having said this, slurry bubble column also have its usefulness in other significant industrial application. For example, it's been used in methanol synthesis. It's been used in the catalytic synthesis of organic chemicals and for the conversion of glucose to sugar alcohol. Um, on the picture, we have a commercial representation of a slurry bubble column reactor for Fischer-Tropsch synthesis. So this reactor was designed by Sasso. It is used for the production of liquid fuel and chemicals from syngas. So in the Fischer-Tropsch process, this type of reactor is preferred to the other three reactors we earlier mentioned because it has an excellent heat mass transfer. It has a low pressure drop, and it makes use of fine divided catalysts, and it also has a very high yield per reactor volume. Because it's a simple structure, because of this simple structure, its construction and maintenance costs are quite low. However, there are some challenges associated with this kind of reactor. So one of the problems is the problem of back mixing, and also the difficulties encountered during the process scale-up and the design of this reactor due to its complex hydrodynamics. So we'll be here we're trying to compare the fixed bed reactor with the slurry bubble column reactors. Like I said earlier, the slurry bubble columns has a very, very excellent heat remover.
Obina, one comment. Try to make the transition smoother. So go back and
All right.
go back one slide. So here you're saying, okay, this is a commercial scale slurry bubble column reactor used for Fischer-Tropsch synthesis. This is in Sasol. And as you can see, this is a very big vessel. It's 10 meters in diameter, 60-meter high, and can produce 34,000 barrels per day. This comes with a lot of difficulties. And now we're going to talk about some of the advantages and disadvantages of this reactor. And then you move on. Try to keep some sort of transition so that you're just not breaking, especially in the initial slides, because really the first, maybe you have 20 minutes, the first 7 minutes are very important because you want to give them a good impression. And then usually, they'll start zoning off, they'll start, sleeping. And then you want the very beginning to be very good and the end to be very good. Okay?
Okay. All right. So I should talk about the advantages in the next slide instead of try to incorporate it here.
Yeah. So just repeat this slide now.
Okay.
Just repeat. Talk slowly again.
Okay.
Just talk slowly, talk confidently, and yeah, you'll be fine. So let's try it again.
All right. So okay. So the most popular application of slurry bubble column reactor is in the Fischer-Tropsch process. As you could see on this slide, this is a commercial slurry bubble column reactor by Saxo. It is used for the production of liquid fuels, chemicals from syngas. Basically, this kind of reactor is usually the reactor for choice for Fischer-Tropsch process because of its numerous advantages. However, there are some challenges associated with the bubble column reactor. So one of these challenges is the problem of back mixing and the problem encountered during the scale up and design.
Yeah, but move on to the next
of
slide.
The reactor. Okay.
Yeah, so now you can, once you talk about adventure, show this slide and talk about it, that they can see what you're saying.
All right. Okay, so I'll be alternating between them. Okay.
Yeah, no, you're just trying. This is transitioning. Saying a story. You don't want to have a jump between one slide and the other, right? You want to keep them. You're just telling a story. Make a smooth connection.
Okay. So when comparing other reactor, in this case, we are trying to compare the fixed bed reactor with the slurry bubble column reactors. We found out that the slurry bubble column reactors has a good number of advantages. One of which it has a very excellent heat removal process. It makes use of fine catalyst particles. It has a very, very low pressure drop. It gives a very, very high yield per reactor volume when compared to the other reactors. And it has a low construction and maintenance cost. As earlier said before, we had the major challenges associated with this kind of reactor are one, the problem of back mixing. It has a the liquid solid separation is quite challenging, and the difficulty in modeling and troubleshooting this kind of reactor due to its complex hydrodynamics. So we'll be seeing how we're going to model this kind of reactor in the next slide. So in the modeling and designing of a slurry bubble column reactor, it requires a reliable prediction of the volumetric mass transfer coefficient. So this coefficient is usually a function of the hydrodynamics characteristics, which are the gas holdup, the bubble size, the regime transition velocity, and also the gas diameters. Also, these characteristics are influenced by the physical properties of the gas, the solid and the gas, the liquid and the solid phases, which are the catalysts. It's also influenced by the operating parameters, the pressure and the temperature, and it's also influenced by the reactor design parameters, the column diameter, and the distributor. So there are quite a number of factors affecting the hydrodynamics of a slurry bubble column reactor. The factors are liquid surface tension. No, okay, we just basically we have three factors affecting the hydrodynamics of a slurry bubble column reactor.
Just take a second. Okay, so the previous slide was okay. You said go to the previous slide. So you said, okay, when modeling SBCRs, we have a lot of parameters we have to account for, you know, hydrodynamics, you said all of this stuff. And then you move on to the next slide. And you say, so this schematic here shows all of these parameters right here. And as you can see, in order to determine these parameters, on the right-hand side here, we have the gas holdup, KLA, and yes, these parameters are actually a function of many other parameters, such as the physical properties of the gas, the liquid, and the solid, the design of the reactor, the operating conditions, etc. Right? So yeah, just take it slowly and try to yeah, just you know, transition it this way, I think.
All right.
So just repeat it again from the previous slide.
All right. So the design and modeling of a slurry bubble column reactor, it requires a reliable prediction of the volumetric mass transfer coefficient. So this coefficient is a function of the hydrodynamics characteristics, which are the gas holdup, the bubble size distribution, flammability, and the bubble diameters. So these characteristics, these hydrodynamic characteristics, are further influenced by the physical properties of the gas, the liquid, and the solid phase, which is the catalyst. It's also influenced by the operating parameters, the pressure and temperature, and also by the diameter of the column. So the next slide, we have a schematic showing the factors affecting the hydrodynamics and mass transfer parameters in a slurry bubble column reactors. So basically, the factors affecting the hydrodynamics are the gas holdup, you have your liquid mass transfer coefficient, I have your diameter of slurry. So these three factors are also affected by the physical properties of the gas, which are the density of the gas,
That's fine. You just say
the wettability.
You just say physical properties and move on, because you know you don't want to, you know, we're already 10 minutes, and yeah, just say physical properties and move on to the next slide. But good, yeah.
Okay, 1, 2, 3. Okay.
Repeat the previous slide, Abina. Sorry, repeat the previous slide, and then let's move on.
All right. So which is this one? The factors affecting the hydrodynamics.
Yeah, this one. So you say, you know, the hydrodynamic parameters. So this schematic shows all the different parameters. So as we said, the hydrodynamic parameters, the gas holdup, KLA, and DS. And these are a function as well of the physical properties of the gas, liquid, solid. They're a function of the reactor dimensions and a function of the operating conditions. So three things: functions of the physical properties, gas, liquid, solid, function of reactor dimensions or reactor design, and also a function of the operating conditions of my reactor.
Okay, pressure and temperature. All right. So I'm gonna link this one now. So we've talked about
Go back, Obina, repeat it, please.
Okay, I should repeat it.
Yes.
All right. So on the slide here, we have a schematic showing the physical properties. No, sorry, we're showing the factors affecting the hydrodynamics in a slurry bubble column reactor, which are the gas holdup, the liquid mass transfer coefficient. So these are in turn affected or there are functions of the physical properties of the gas, the liquid, and the solid. And these also are also affected by the operating conditions of my reactor, the temperature, and the pressure
And the reactor design.
on the reactor design.
Yeah. Okay, good. Move on to the next slide.
Okay. On the slide here, we have different resistances in three-phase system. The formula in calculating the total resistance in a three-phase system is given by this equation below. Here we have a mass vapor pressure which is nearly equals to 0. We also have
Okay, one thing,
fine catalytic
Dina,
particles.
pause for a second. So here, this is what you say, okay? So when we look at the three-phase system, is okay, this schematic here shows you have a gas bubble and then you have a catalyst, right? So now you're pointing at the gas bubble and the catalyst, you say. So in order for the species to move or to react, the species or the molecule has to diffuse from the gas bulk to the gas liquid interface, and then from the gas liquid interface to the liquid bulk, then from the liquid bulk to the liquid solid interface, and then finally move to the catalyst particle to react. Okay, does that make sense?
Yeah.
So again, I'm saying the molecule will have to diffuse from the gas bubble through the gas liquid interface. You see the blue written here, gas liquid interface at the top.
Okay.
Through the gas liquid interface, and then it will get into the liquid bulk, which is, you know, the bulk of the liquid. And then it has to move through the liquid solid interface. You see it at the top here written above this, above the circle here. Liquid solid interface, and then finally reach the catalyst particle for the reaction to happen. Okay? So if we write the overall, so sorry, you can say on, and then you move on to the right here, the blue equation. You point to the blue equation, and then you say, so this equation here shows all the resistances. And as you can see, I have resistances, the gas, I have gas resistances, I have liquid resistance, and I have solid resistance, in addition to the reaction diffusion resistance, right? So these four elements, Kg is basically your gas phase resistance, right? Kl is the liquid resistance, Ks is the solid resistance, and this K note, and this is your Thiel constant, this is a catalyst, or, you know, the reaction resistance, okay? And if we look, and then you say, if we look at all these resistances, we can eliminate some of them. So we can eliminate the gas phase resistance because the wax vapor pressure is 0. This wax is heavy. Okay. Then you can say we can then eliminate. We can also eliminate the solid resistance because, you know, the catalyst particle is very fine. So I can eliminate the Ks. And then you can also say, you know, I can also assume I have very good mixing, etc. So if I eliminate these two resistances, you look at the bottom red here, at the bottom left red equation, bottom left, the box, the pink box. You see, so if we eliminate the Kg and the Ks, you can find out that the resistance in this system only depends on the KLA, which is the liquid side mass transfer coefficient, and the reaction kinetics. K naught is your reaction rate constant. So this is the point you want to make here, right? You want to say that, you know, this molecule has a long trip, has to move from the bubble to the liquid to the solid, you know, it has to travel through many things until it finally reacts. And from when I look at all these resistances, when I look at all these barriers, only the KLA really and the reaction kinetics control this resistance, because the other two are very small, right? This is what you want to convey.
Yeah.
Okay. So
all right. So
go ahead.
When you said the gas bulk, can I also say the gas thing, or do I mean a different thing?
No, yeah.
Like
So
when you are like the gas bubbles and goes through the gas liquid interface.
Yeah.
Into the gas bulk.
Yeah.
Into the liquid bulk.
Liquid bulk. So the middle of your bubble is the gas bulk. The middle of your liquid is your liquid bulk. Sorry. And between them you have your interface. And this interface is made of the gas film and the liquid film. Okay. You can say it whichever way you want, but just go through it slowly and make the point clear to the people listening.
Okay.
Okay, so let's repeat it slowly. Maybe take your time and just say this information, and then when we practice again, you'll have some time to prepare notes or something to do to say. Let's repeat
Okay,
this
for
slide.
it. Yeah. All right. So these slides shows the schematics of different resistance in a three-phase system. Here, the gas bubble diffuses and moves through the gas liquid interface to the liquid bulk. Then from the liquid bulk, it goes through the liquid film and comes through the liquid solid interface to the solid bulk.
No.
Then it goes all the way
One
to
second. You say the species or the molecule goes from the gas bulk to the gas solid interface and then moves to the liquid bulk. It's not the liquid film, right? Just be careful with the order. So the liquid bulk is after the liquid film, right? Liquid bulk is basically the space between the two circles, the space between the gas bubble and the catalyst particle. Okay.
Catalyst bubble. All right. So it has to be it moves from the molecules.
No, the molecule moves from the gas bubble.
Okay.
To the gas liquid interface.
Perfect. To the liquid bulk.
And then to the liquid bulk is outside the circle.
Yeah.
This is the liquid bulk, yes. Liquid bulk is the space between these two.
Okay.
And then from the liquid bulk, it goes to the liquid solid interface. And then from the liquid solid interface, it goes to the catalyst particle.
Oh, particles catalyst. Okay.
Okay, let's try it again.
All right. So this is a scheme showing the resistance in the three-phase systems. Here, molecules move from the gas bubble and it goes through the gas liquid interface to the liquid bulk. From here, the molecules here diffuses and goes through the goes through the liquid solid interface and goes through, then the species, this is confusing.
Oh, it just goes from the liquid solid interface. Now it's on the solid, right? It's at the catalyst. It reacts at the catalyst, right?
It's a catalyst, then reacts to the catalyst.
Yeah, because once the molecules hydrogen CO they get in contact on the catalyst surface, they react.
Okay.
That's it. So after this liquid solid interface, it reaches the catalyst particle, and the reaction happens. That's it.
Okay. From here it goes from here. Can I skip this slide and prepare for it tomorrow? Because I'm
okay. That's fine. But just organize your
okay.
thoughts, speak slowly,
Yeah,
and you'll be fine. That's fine. Okay, let's move on.
Okay. All right. So let's state the current state of knowledge we know about our modeling of our slurry bubble column reactors. One dimension and two dimension empirical models for the slurry bubble column are available in our literature. So these models, however, are not capable of predicting the hydrodynamics, which are the gas hold-up, our velocities, and our solid distribution in slurry bubble columns, often provided with different internals. So few computational fluid dynamics models are available to predict this local hydrodynamics and gas velocity, which will explain the overall behavior of our slurry bubble column reactor. these computational fluid dynamics models have not been validated using air-water systems at ambient conditions. Thus, there's a great need to properly validate our computational fluid dynamics model to predict the hydrodynamics and the overall behavior of our slurry bubble column reactors for Fischer-Tropsch processes. So we're talking about the different hydrodynamics regimes in slurry bubble column reactors. So when taking a closer look at the hydrodynamic regimes.
One second, Obina. Go to the previous slide, sorry. Okay. Okay, just how would this remove dynamics?
I should remove this?
No, the last point, just change it.
All right, this one.
Yeah. So just say there's a need. So there's a great need to get a better understanding of the local phenomena inside the SPCR. Okay.
Okay. So there's a great need.
Yeah. Here. I'm gonna write it in the chat. The last point, just change it to this. There is a great need to develop more representative understanding of local. Okay, I put it in the chat. Just change the last point to this, because this will make it easier to transition to the next slide, right? So you're going to say we're talking about local phenomena. Now let's talk about the flow regimes.
Yeah, the flow regimes. Okay, to the chat. All right. Okay. So let's talk about the current state of knowledge we know about in modeling our slurry bubble column reactors. So we have one dimension and two dimension empirical models for our slurry bubble columns. They are available in the literature. So, but these models, however, are incapable of predicting the hydrodynamics, which are the gas holdup, the local velocities, and our solid distribution in our slurry bubble column reactor. Few computational fluid dynamics models are available and are able to predict our local hydrodynamics, which could help explain the overall behavior of slurry bubble column reactors. But the problem is our CFD models haven't been properly validated using air-water systems at ambient condition. Thus, there's a great need to develop more representative understanding of local phenomena in our slurry bubble column reactors. Let's talk about the different hydrodynamic regimes that exist in our slurry bubble column reactor.
Good.
When taking a closer look at the hydrodynamics regimes in slurry bubble column reactor, we could see three different flow regimes. We have the bubble flow, the plug flow, and the turbulent flow. So different parameters like our superficial gas velocity, our liquid height, and our solid concentration affects our flow regimes. So the homogeneous or the bubble flow is the most widely investigated regime, and it usually occurs at low to moderate superficial gas velocity. It is usually characterized by uniformly sized bubbles traveling vertically with minor interactions or with no oscillations. And there's practically no quiescence, sorry, there's practically no quiescence and breakup. So by this we mean all bubbles rise up at the same time. Hence, there's a narrow bubble size distribution. The gas holdup is radially uniform. Therefore, bulk liquid circulation in homogeneous regime is insignificant. The size of the bubbles in our homogeneous regime depends mainly on the size of the gas distribution and the physical properties of the liquid. Let's go over and talk about our plug flow regime. So as velocity increases and rising bubbles increases and induce movement in our slurry or in our liquid phase, plugs are formed. So when the velocity increases and small diameters are gotten, we usually have a plug flow or a slug flow regime. But when these bubbles, the velocity increases, then our large we have a heterogeneous or a Chern turbulent regime because of the large diameter. So the plugs of gas in the liquid phase, where the velocity is assumed to be constant. So why the plugs are bullet shaped, they cover most of the cross section of the core column. So moving on to the last one, Chern turbulent flow regime or our heterogeneous regime. Our heterogeneous regime is characterized by the recirculation from rising gas bubbles. So this flow or the Chern flow occurs at a very high gas superficial velocity um, due to its intense coalescence and breakup. Small as well as large bubbles appear in the regimes. So it leads to a wide bubble size distribution against a narrow size distribution for our bubble flow. These large bubbles through this liquid bubbles up through the liquid, and thus it is called a Chern turbulent flow. There is enhanced misting in our Chern turbulent flow. Our Chern turbulent flow has a very high heat and mass transfer coefficient, and the solid phase is easily fluidized with a more homogeneous distribution. So the different flow regimes and the transition velocity affects the transition from one flow to the other. So let's talk about the different the transition flow amongst these three regimes.
Robina, one comment. When you go tonight to practice or to try to organize your thoughts better for the previous slides, you're stopping a lot. You're saying a lot of that's not helping the presentation. It's distracting to the person listening. Okay.
Okay.
So try to organize. Try to avoid reading of the slides, and try to just make it to the point. So this regime was 1, 2, 3 points. Move on. You don't have to read everything on the slide, because I'm saying the slide. I can read everything myself. They will have your thesis. They will have a copy of the slide, so they can do they can do that at their own time. You want to maintain your 20 minutes, and you want to organize your thoughts and be to the point. So organize your notes and organize what you want to say. But for now, let's move on through the slides. Just go on and say what you want. Like present the rest of them. Yeah.
All right. As we could see, the homogeneous and heterogeneous flow regimes have entirely different hydrodynamic characteristics. So such different hydrodynamic characteristics result in different mixing, as well as heat and mass transfer rates in these flow regimes. So therefore, there's a need for demarcation of these flow regimes becomes an important task in the design and scale up of such reactors. On the slide, we have a schematic of a flow regime map for liquid batch bubble column. It was developed or designed by Dekwa, and it shows the different transition from slug flow to your bubble regime flow and to the heterogeneous flow. So there have been some problems with this map because it's not easily delineated, and this map is just based on air-water system. So if you have a different system, so this map is not a good representative of the transition between flow regimes. And one other thing to note is we're only limited to the near wall. We can't see through the column. So there's need for a different approach. Um, the need for this different approach has led to these research objectives. We're trying to find the best way to represent a flow regime map for the turbulent region, since the one previously made by Dekwa was only restricted to air and water systems.
Yeah,
In addition to that,
you have to work on this transition. This transition was not good, right? It was just it was not smooth transition, So the point you're trying to make is, so you talked about the flow regimes, and now let's talk about the transitions between these flow regimes. You say at the moment there's only one flow regime developed by Deckware. This flow regime map is very is theoretical. It's qualitative, and it cannot really be used effectively for any design purposes or um, any sort of design or modeling applications. It just gives me a very general pattern. And a limitation of this map is that it's based on visual observations. So because I'm only using my eyes to look in the reactor to try and find it, I'm only seeing what's happening near the reactor wall, right? I'm not seeing what's actually happening in the middle of the reactor. And this map fails at higher solid concentrations, so at solid concentrations greater than 5%. This map fails, so we need to find a new approach to better represent this. And this is the objective of this work. And now you move on to the next slide. So the objective of this work is, now you move on to the next slide, Abina, and you say the objective of this work is we want to develop a better understanding or delineate or find the boundaries of this churn turbulent flow regime. So we did this by analyzing over, so I would change the slide. So I would say, so the objective of this, I'm going to write in the chat, is to develop a clearer delineation of the different hydrodynamic regimes, right? In order to do this, we analyzed over, and then we say the same thing, okay? So change the slide later on this way. So we say, so now the objective is we want to get a better understanding of these different regimes. How can we present them? And this was the purpose of this work. And this is what I did in this work. I looked at over 400 experimental points of different pressure fluctuation data, and I used them to determine the boundaries of the flow regimes. Okay, this is how you see. Did you see how the story now is smoother? Yeah. So this way you want to minimize the jumps, because the moment you jump, the committee will go, oh, I don't get this. It might stop you, might ask you questions, it might, it might drag on, and you want to be in control of the story. So you want to say the story in a clear way. Okay? Okay, let's move on.
Oh, so I need to talk about this pressure and matrices. Um, so in trying to, so, like you said, I analyzed over 400 different data sets, and I use the principle of pressure fluctuations to do this. So this analysis has been previously done. Uh, the frequencies of the fluctuations indicate a change in the hydrodynamic regime. When there's a change in the frequency, it indicates a change in the regime. These fluctuations depends on the gas velocity, uh, the pressures, and the catalyst concentration. So my work was to try and find the different pressure fluctuations for my 370 data sets. I The method I used in doing this was I used experimental data. So let's take a look at the experimental data used in this analysis. This data was provided by Dr. Moses Group at the University of Pittsburgh, um, and the data was measured in a pilot scale slurry bubble column reactor. The reactor used has a 3 meter. No, the reactor used was 3 meter high with an internal diameter of 15 centimeter. The reactor operated within the Fischer-Tropsch operating range with temperature between 320 to 500 Kelvin and pressure within 4 bars to 31 bars. This experiment shows, or sorry, this experimental data show different data for different gas, liquid, and solid system. Um, this is a schematic of the experimental procedure. So usually these experiments are done using two main methods. The first one is called the manometric method, where we measure the pressure drop within 2 points in the reactor. And the second method is called the dynamic gas engagement, where I let the reactor reach steady state and stop the gas flow, and I monitor the pressure drop along the reactor with time. So I'm trying to find the time it takes the bubble to disengage, and I can make different extrapolation about the nature of bubbles from this data.
Good.
How is it opening? Um,
What's happening? You're missing something?
I don't know. This one appeared twice.
Oh, that's fine. It's fine. I can clean this later.
Okay. All right. So from our experimental procedures, we generated the pressure fluctuation data. So this data is not directly used, but it's being measured for each experiment. So we inspected these different pressure plots so that we could try and get some trends. But getting anything from this pressure fluctuation is not easy. So therefore, we needed a better approach to translate these pressure fluctuations data. This is where the power spectrum density analysis come into play. So before we talk about the power spectrum density function, let's talk a little about signals. So signals can be classified as periodic and non-periodic signal. So for periodic signals, these signals repeat itself over a fixed length of time. The signals could be deterministic or random. Usually the deterministic signals can be characterized mathematically in a time domain, while the random signal is specified in a probabilistic description. So in the case of an arbitrary waveform or wave shape, so this is the case with the pressure fluctuation we've seen earlier in the previous slide. So these fluctuations are random signals, and we can't really use Fourier signals to analyze them because Fourier series itself is a periodic function, and our signals are not periodic. They are non-periodic, so we can't use Fourier series to analyze them. So the concept of power spectrum density is used to determine, or is used for such indeterministic signals or such non-periodic signals. So the power spectrum density function. So the power spectrum describes the distribution of power versus frequency. By using this formula, we could compute the average signal power, where our power is given by 1 over 2 pi integration negative infinity to infinity of this. So in my power spectrum density plot, the power or strength of these variations are functions of frequencies. So the frequencies at each variations are strong, then the frequencies at which the variations are weak are also displayed. So this plot, it shows us the strength of the variations as a function of frequency, and it kind of shows us where the variations are strong and where the variations are weak. The unit of my power spectrum density was energy per frequency, which translates to watts per hertz. So many approaches have been employed for the analysis of pressure analysis. So approaches like Fourier transform analysis, frequency domain analysis, wavelet analysis. But what I did here was to translate this random pressure, signals into PSDF plots using an automated MATLAB algorithm. So once I did that, I came up with 376 feasible PSDF plots. You could see them here. And this is what the plots look like. Basically, you could see the power spectral density versus the frequency. The basis for my study was focused on observation from previous work, which were low frequencies corresponding to large bubbles. So in the case where we have low frequencies, it corresponds to large bubbles, and a wider frequency distribution observed for lower catalytic concentration. So if we have a low catalytic concentration reaction, we was observe a wider frequency distribution. The next step I did was I did a visual analysis on this power spectrum density function plots. So upon visualization, I grouped them into 3 main groups according to their frequency strength. Group A had frequencies from 1,000 to 10,000 hertz. So these groups correspond to the growing bubble regimes, where I had a majority of small bubbles. The group B had frequencies from hundreds to 1,000 hertz. So this group corresponds to the bubble transition regime. Then the group C corresponds to the bubble transition regime. So the group B had frequencies between 10 to 100 hertz. The representation below shows the stable bubble regime. Large bubbles are much here. Then here it shows the growing bubble regime. Like small bubbles are predominantly here. And when we move down, when we move up the column, or we'll find out that we could see a bubble transition regime. where they're transiting. So after doing that, the spectral analysis was measured, and it revealed the following. It revealed the following three types of power spectrum densities. So the first one was we had a wideband low amplitude spectrum, which is mostly associated with bubbly flows, a wideband flow amplitude spectrum. We also observed a low frequency peak of large amplitude. It corresponds to the characteristics of a slug flow. And the last one we observed was a medium width band spectrum for heterogeneous flow. So this was what our spectral analysis revealed to us. So after grouping our PSDF plots, I looked at the experimental and operating condition corresponding to each group. So these conditions were used to characterize each PSD groups. Conditions like bubble velocity, interfacial area, pressure, temperature, and gas hold up. So these operating conditions, it gives us an idea on how our flow map regime is going to use. So we're trying to find out what two parameters are we going to use to make our flow regime map. So these are just some generalized results. This table shows the superficial gas velocity of our different groups. So it shows the pressure and as well as the temperature of each of the PSD groups. Also some generalized results. It shows the gas hold up, both for the small diameter and the large one for different groups. Let's all do.
When showing your results, you need to take some time. So when you show the previous slide as well, you're gonna say, so I divided into three. You don't just say, oh, this is a generalized results. No, say, okay, so now I have three groups, A, B, and C. Group A falls in the superficial gas velocity from 0.195 to 0.208, pressure of 166 to 2.1, temperature of this. Group B, same thing. Group C, same thing, okay? And I think it's better if we present this as a figure instead of a table. Okay, move on to the next slide. Similarly, say, okay, now if I want to classify them in terms of gas holdup, you can see, group A, this is the gas holdup distribution actually. Group A has a gas holdup distribution of up to, or you can say, there's not a big difference in the way the three of them represent the gas holdup. And then I'm not sure what you want to say on the volumetric mass transfer coefficient, but we need to change the slide somehow. And then we also need to add a slide for conclusions. Okay.
Okay, and now, since we're trying to develop the flow map regime, so I was thinking, what parameters are we going to use?
Yeah. I was thinking. I mean, if you can come up with something this week.
Yeah, I was thinking of because I found a correlation of volumetric mass transfer coefficient. I think it's experimental data, and they gave different values. So if I could get the diameter, can I represent this flow map regime in terms of the diameter of the column and the superficial gas velocity?
Yeah, you could do that. Yeah.
If I do that,
Yeah,
okay.
if you can do that, that'd be good. So and we also need to add a slide with conclusions, just main points. So you're gonna say, we wanted to develop a flow regime map. We used PSDF, just 4 or 5 points summarizing what you did, and this will be the conclusion slide before the thank you. Okay, so let's stop. Let's stop here for now. like a few things. Just please let tonight practice what you want to say. Think about the transitions and these things. It's very important because at some points the transitions were not very good, or the story was not very smooth, especially at the beginning. Once you got to the middle of it, you were good and everything was fine. But the very start, it was very shaky, to be honest with you. So tonight, rehearse with yourself. Think about what you want to say. Try to say the story, what you want, and be aware of the time as well. Because I think now um, maybe we're over 25 minutes. So maybe try to, at some slides, you don't want to spend that much time, but you want to be efficient. Okay, so tonight when you rehearse or when you practice, just think about these things and practice with yourself a few times, and then tomorrow we'll rehearse again together. Okay.
All right, thank you very much.
One more thing, Obina, please send me all your Excel sheets and any write-up you have. Just email it to me today. Okay.
Okay. Okay. My Excel sheet. Do you mean the data sheet you sent to me?
No. Any type of work you have, any whether
Okay. Okay.
just send it to me. Okay.
Okay.
I want to have a look at them because I want to add a couple more slides at the end for the results as well, right? Okay.
All right, thank you.
Sounds good. All right. Okay, Shemeka, whenever you're ready, share your screen and let's rehearse as well. Yeah. Sorry. Did you convert it to PDF or is this PowerPoint?
PowerPoint.
Okay. So whenever you're ready, start.
So I changed the name to so it can correspond to the citation.
Okay, sounds good. That's fine.
Okay. I'm trying to. Hold on a second.
No problem.
I'm trying to get the highlight button so that I could use to talk.
Which button? You mean the laser pointer or what?
Yes, the laser pointer, yeah.
You right click on the slide and then you should have pointer options or something, and one of them should be laser pointer, something like that.
Okay. Okay, I'll send it. Okay, let me share now. Can you see the slide now?
Yes, I can see it. So whenever you're ready, just start.
Okay, if I'm ready.
Okay.
Good morning, everyone. Thank you for coming for my thesis presentation. So I'll be going. So my name is Chiemeka Chukudor, and I'll be presenting the optimization of microreactor design using computational fluid dynamics, which is the CFC. So first and foremost, this will be the agenda of the thesis overview. I'm talking about the introduction, empirical work, methods, results, conclusion, and the current and future research. So yeah, I have a lot of slides to present in a short amount of time, so I'll briefly explain each slide quickly and move on to the next slide. And at the end of the day, we'll be discussing the questions at the end and address any informations. So the idea that brought me to this research study was basically about the microreactors, which have attached significant figures in recent years of study because of the ability to leverage the reduction of heat and mass length scales to maximize process productivities and to deliver major benefits to the industry.
Are you moving the slides? It's still stuck.
Yeah, I know.
Okay.
Yeah, I'll just briefly introduce the topic.
Okay, good.
Yeah. So these are different on the background, different ongoing works on experiment by other people and the process of modification, having smaller reactors that helped to provide larger scales operations, having the mass transfer problems and heats, which are also cheaper and you can always try to move around it. So here it's the lab setup, and this how this is being set up in the lab, having the various components, having the inlets and outlet flows of the two gases going through it. Then we have the lab view computer. This is where the simulations are being done, and the setup is in Hanks Hall, and that's where the work was being done in small scale.
Yeah, Shamika, I have to be clear. This is where the experimental work has been done. Not our modeling work was not done there, right?
Experimental work.
Yeah, this is where they do the experiments. We don't do the experiments. So, your work is not experiments. It's the modeling work.
Oh, okay. So on the background, so this this talks about the experimental activities that have been done before. Nafiz has done the work before, and Dr. Kuli, and it was about the effect of merciful silica support and on the Fischer-Tropsch study using the catalyst and makings of the 3D printed stainless steel reactor. So here the process intensification one, we're trying to find a smaller transportable process units, and it's based on to reduce the dimension and to enhance the heat and mass transfer, and also hold on one slideshow.
Shamika, I don't like this transition, to be honest. So after talking about the experimental, just saying, so the first few slides you want to say really is there's experimental work being done, and this is their experimental setup. They looked at catalysts and the motivation behind process intensification. And then when you transition to the slide, you start saying motivation behind process intensification and modularization is we can have better height and mass transfer. It's safer. You can transport the units, etc. Okay, try to say it in a story way and try to change your tone because the way you talk is your tone is very steady. Okay, try to maybe have some pauses. Change your tone up and down a bit so that can keep the committee engaged. Right. Otherwise, they start to drift away. So you lose them, and then at the very end, you find them asking all the questions again, which you already presented. Okay.
Okay. Okay. So yeah. So the process intensification and modularization deals with the enhancing the heat and the mass transfer, represents intensive safety and oh shit. My slides keep moving without me moving them.
Okay. I think if we have some setting in escape and
Yes.
in
let me
PowerPoint
skip.
at the top, if you just close out of this presenter mode, okay.
Yeah.
At the top, you should have an option, which, wait, let me open PowerPoint and find it. There should be an option which says, move automatically. You need to uncheck it.
On the top.
Yeah, let me see. Let's see. Where is it? Okay. On transitions, you see transitions in PowerPoint. You have at the top. On the right-hand side, you have advanced slide. What do you see? You see on mouse click, and then there's after something, right?
Where?
On the transitions tab on the right-hand side completely, you should see something advanced slide. Yeah, you see on the right. No, move to the right more. More. Yeah, there. Yeah, yeah. This just uncheck after. On the left of the Sabina. Shamika, sorry. Left. Yeah, just uncheck after only on mouse click. There you go.
Okay. Okay, that's fine now. Okay. It's still repeating itself. It keeps doing it.
Shamika, you need to uncheck after. You see at the top here, you just keep it on mouse click only. Yeah, this way you only transition on mouse click. So try to present. No. Oh, you have it for all the slides. Okay.
Oh, that's for me for all the slides.
Yeah.
Oh shit.
Okay, it's fine. I mean, we have more time for you because you're presenting next Thursday, right?
Yeah.
So just change it and practice. Keeping all these comments. So I also said to Obina, try to say a story, try to keep it smooth, try to control the transitions, all of this stuff. And what's a good time for you guys tomorrow to meet? How about 2 p.m. for us to meet again and rehearse?
2 p.m. 2 p.m. is not favorable for me, sir.
Well, what time is good for you tomorrow?
Anytime in the morning, but from afternoon time, I'm busy.
You don't have. I mean, tomorrow morning I can't meet. Um, there's no times tomorrow. Obina, are you still there?
Obina.
Okay, maybe I want to do something. It's fine. Okay. What time would be good for you, Shemeka? Just tell me the availability.
I'll be free in the morning hours, sir.
Okay.
From 2 o'clock on, I'll be busy.
From 2 on, you'll be busy. Okay. Let's
Yes,
let's
sir.
let's meet at 10 tomorrow. How about that? Okay.
Okay, 10 is fine.
And then fix all your slides. Practice a few times by yourself. Try to limit
Yeah,
it to 20 minutes and try to say a story. And try to control the tone. Yeah, don't try to keep it very monotonic all the way. This way, they're gonna get, or the committee will get bored, and you want to keep them entertained, right? You want to keep them happy. That's it.
yes,
Okay.
sir.
So let's try again tomorrow, and I don't know where Rubina is, but when he comes back, or maybe he'll send an email saying that we'll meet tomorrow.
Okay.
If he can't make it, so me and you we can rehearse, and then I'll rehearse with him at separate time. It's fine. Okay.
Okay, that works for me. That's fine.
Sounds good.
Yes.
All right.
Okay, thanks. I'll correct them and practice today and know and understand it properly.
Yeah. Sounds good.
Then by tomorrow I'll be able to deliver it well.
Yeah. Sounds good. All right. Thanks, Shemeka. Thanks, guys.
Okay, thank you, sir.
Talk to you.